So today we'll talk about two topics. We will talk about different kinds of numbers, and not just the real numbers, but of the complex numbers as well, and the abbreviations for all of those. So we've done a little bit of that. We're also going to talk about if you have a repeating decimal, how do you change it to a fraction? Some we know. What is 0.33333333333333333? I should see hands going up. Jonas. 1/3. But there are a bunch of them that we don't know. I might have 0.123, and we'll get a method for how we could convert that to an actual fraction. So first are different kinds of real numbers. The first ones that you start out learning when you're an itty bitty kid, how to count, right? 1, 2, 3. And then do you remember being really proud of yourself, or maybe seeing a younger sibling or niece or nephew or cousin really proud? They can count all the way to 10 or 20 or 100, and they're wanting to show off because they can keep going and going. Those are the natural numbers. And if you want, you can use a double-barred N as an abbreviation for those. Those would also be the positive integers, right? So we could also call those Z plus, because they are simply the positive integers. Okay, the next bigger group, we are going to take those and keep all of those, and we're going to add 0 into that. Because again, as a little kid, it doesn't take very long before you learn the concept of none. Maybe you learn the word 0, maybe you don't, but you want a cookie and they're all gone. So you learn the concept of 0. What do we call the numbers 0, 1, 2, 3, 4, 5, 6? You guys should know this one. But those are indeed the whole numbers. So that's our next biggest subgroup. If we add 0 in there, we call those the whole numbers. And so I'll put a bigger circle around all of that, maybe. So if we take all of those, let's see, maybe I can pull my word down here. If we just add 0, then those are the whole numbers. And we don't really have any good letter for that. I'm not sure why not, we just don't. Okay, then a little bit debatable of which ones you might go to next, but we're going to go with, let's throw in the integers. We've got all of the positive integers up here already because those are the natural numbers. We've already got 0 up here. So if we take the opposites of everything that we already have, then we will have the integers. So that circle includes all of the ones that we've already had. So I'll draw it all the way around everything we've already had. And then we have the integers, and we know we can label that with just the double-barred Z. And that's when we also add in the opposites of all of the whole numbers. So now we have ... -3, -2, -1, 0, 1, 2, ... going forever and ever. And that concept comes in about the same time as rational numbers do. It's really, really cold, and it's too cold to go outside and play, or you try to go out and play in the snow and you're freezing and uncomfortable because the temperature is below 0. And whether you really talk about it and learn the negative numbers or not, at least you got exposed to the concept of it being something really, really lower than 0. Then when we throw in fractions, what do we call those? Ted? If we throw in all of the fractions, then we have our rational numbers. So let's bring a bigger circle up here and a label for this one. So rational numbers needs to include everything we've already put up here. And we're going to throw in now all of the fractions, which also means all of the decimals that end and the decimals that repeat. And you learn that concept pretty early on. There's one cookie left, and you and your brother both want it, and mom says we're going to split it in half. And so you each get half a cookie. And our symbol for rational numbers is not the double-barred R. It is a double-barred Q, or a Q somehow with putting a weird line through it like that. And that Q comes from, it can be written as a quotient. Okay, if it is not rational, there are numbers that aren't rational, right? And so we put the prefix in front of it that says not, which is irrational. And that has no overlap with the rational numbers. It is either rational or it's not. And who can give me an example of an irrational number? Charlotte? Pi. At first I thought you said 5. I was going, what? Yes, pi is a good example of an irrational number. It does not end. It does not repeat. It cannot be written as a fraction. What else is an irrational number, Elizabeth? I is also, well, no, actually, I is not irrational. It's imaginary. And we'll get to that in another group. It's not real. Right now, we're still just doing reals. All irrationals are reals. So square roots that cannot be simplified. If I wanted the square root of 16, that is 4, so that is a whole number, even if I write it in a weird form. Now, if we take all of the rationals and all of the irrationals, those are our real numbers. So this red circle needs to include all of the rationals and all of the irrationals, and those are all reals. But as Elizabeth just reminded us, and as we've learned previously, there are numbers that aren't real. There are ones that have I in them. We can have ones that are 100% imaginary. And let me get these circles up where we can see them on here along with everything else. So completely separate from the reals. We can have imaginaries. These would, strictly speaking, be ones that are 0 plus something times I. So I could have I. I could have 5/7 I could have -4 I. Something times I, but no real part on it. If we have both parts, real and imaginary, those will be our complex numbers. Almost there, and then this will finish up our picture here. And then we'll make sure everybody has all of those written down somewhere in their notes. And so complex numbers would have a real and an imaginary part. So 3 minus 2i, 1/2 plus 2/3 I. The real numbers, I could say, are all something plus 0 I. Sabrea. Imaginaries have the I in them. And if it's strict, and a lot of times we do confuse the vocabulary, and we say imaginary when we mean complex. I'm not going to be real strict on that, but I want you exposed to what the difference is. And I do want you to understand that real numbers are something plus 0 I, but we could write them that way if there were a reason for it. And next year you'll start seeing some where that makes a difference. So everybody good with all of those? All right, what we're going to focus on now are rational numbers, decimals that either end or terminate, or repeat, so we have that repeating bar in there. If it is written as a decimal and either ends or repeats, so not like pi, we could write it as a fraction. Some of them are easy. I'll call this example -1 because it's so easy. If I had 0.7, what is that as a fraction? Hang on, let's have somebody who hasn't answered yet. How do I write that one as a fraction? What would I need to do on that one, Kevin? 7/10. So think about how would I read it correctly? 7/10. Most of the time we say 0.7, but we know the correct way to read that would be 7/10, right? They could get a little bit harder if they happen to be longer, something like this. And I know that is 623, and I'm not sure what great big word I need to put in my denominator there. But I could figure it out. I know this was the tenths place. Hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 million, 100 millionths. Did I count that right? And so I could say 623 100 millionths. That might be the hard way to do it. I could say, you know, if I want the numerator to be 623, so I need to move the decimal 1, 2, 3, 4, 5, 6, 7, 8 places in there. So I'm going to technically be multiplying my numerator by 10 to the 8th. My denominator of 1 times 10 to the 8th, which means 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and I'd have the same number. Easy enough, right? Let's do one more like that. And then we'll go to the repeating ones. So what would my numerator be here? Anna? 513. So let's count how many times do we need to move the decimal? How many did you count? Need to move it 6 places. So in the denominator, I need a 1 with 6 zeros. And put in my commas, 513 over a million. Can I reduce that? Not in this case, but you always want to check if you can simplify the fraction. If it had been 512, could I have reduced it? Divide everything by 2 and then see if that can be further reduced. So we're good with the ones that end, right? Okay, ones that I think are actually more fun if they repeat. And I'm just going to do 2 of these examples and then we'll do homework. So what we want to start off with is, I'm going to leave a little bit of space, and I'm going to write down my actual number, and I'm going to name it n, is 0.01524. Now, which ones repeat in this? Just the 2 and the 4. The 1 and the 5 don't. So this is 0.015242424, and those 2 4s keep on going. How many digits repeated on this one? 2. So if 2 digits repeat, we are going to use 10 to the 2nd power times n. So 2 digits repeat. So now I'm going to fill in this space that I skipped. 10 squared is 100, since I had 2 places that repeated, 1 with 2 zeros, 100n. So if this is n, if I multiply by 100, I'm going to have 1 point, right? I'm going to write that down carefully lined up with what I just wrote. The decimals have to line up. 1 point, 5, 2, 4, 2, 4, 2, 4, 2, 4, dot, dot, dot. So everybody good with how I got that, even if you don't yet see why, because I have not yet talked about the why. Okay, now what we're going to do is to subtract top row minus bottom row, and you see why I skipped the space so I could get my bigger one on the top. What's 100n minus 1n? 99n is, now when you do column subtraction, which side do you start on? Start on the far right, don't you? All right, so all my dot, dot, dots are going to be 2 4s that match up forever. So when I'm subtracting all of those, I've gotten a whole bunch of zeros. And then I get to here, the 4 minus 4 is a 0, the 2 minus 2 is a 0, the 4 minus 4 is a 0, the 2 minus 2 is a 0, 4 minus 4 is a 0, 2 minus 2 is a 0, and then I get here and I don't have zeros. Now I do my regular subtracting. 4 minus 5, I need to borrow 1, so that's a 1. What's 14 minus 5? 1 minus 1, can I do that? Yeah, 1 minus 1, 0. If it had been 1 minus 2, I'd have to borrow again, but 1 minus 1, I'm okay on. 5 minus 0, and 1 minus 0. But it is 1 point, all of that, right? So a couple things that I still need to do. If I want just what is my number as a fraction, instead of 99n, I am now going to divide both sides by 99. And all of these extra dot, dot, dots out here really don't make any difference, do they? And neither do all of these zeros out to here. So I'm really just interested in that 1.509 over 99. But 1.509 is a fraction, just written in decimal form, and I can't leave a fraction inside a fraction. So what I'm going to do is I am going to move the decimal 3 places in the numerator, which means I also move the decimal 3 places in the denominator. So I have 1509 over 99 with 3 zeros after that. Can I simplify that fraction? Okay, explain to me hard way of doing it without the calculator. How would I recognize I can reduce it? Grayson? So you're doing 1 plus 5 is 6, plus 0 plus 9 is 15. That's divisible by 3, not by 9. And 9 and 9 is 18. So we know we can divide both by 3. And we would have what? 503 over 33,000. I don't know if I can simplify that any further or not. Maybe it's divisible by, I don't know, 13 or 11 or something like that. So what's the easier way with the calculator to help you decide if you can reduce it anymore or not, Baylor? Type either one of these in on the calculator, just like that. Don't put a decimal in it, and see if the calculator reduces it any further. Head? And I'm seeing some head shaking. No, can't reduce it any further. So we would stick with the 503 over 33,000, but don't forget to check, because it's wrong if you don't reduce it. Okay, last one. So we start off, we're going to try to find this number as a fraction. So we're going to name it n. And n is, and sometimes it helps to skip over this way a little bit, because when I start multiplying 1 point by 10 or 100 or 1,000, I'm getting some room to be able to line up my decimals. So 1.03, which numbers repeat on this one? Which ones repeat? Everybody? Just the 543. So the 1 doesn't, but then 543, 543, dot, dot, dot. So 3 repeated. So I need to use 10 to what power? 10 cubed, which means 1 with 3 zeros after it. So that means my top row needs to be 1000n, not 100n. Some of them will be 10n, some 100n, some 1000n, 10,000n, just depends on how many repeat. So I need to move this decimal over 3 places, so all the way to there. So I have 1031 point. Make sure I keep lining these up. 543, 543, 543. What do I have on the left when I subtract the 2 rows, Pascal? 999n is. All of these 543s cancel out. These 543s cancel. So do these. 3 minus 1, everybody. 4 minus 3. 5 minus 0. Bring down the decimal. 1 minus 1. And then we've got the 3 and the 0 and the 1 out there. What do I need to divide both sides by? Austin, what do I need to divide both sides by so that I can have just n? 999. Is it okay to leave a decimal inside of a fraction? So I need to move this decimal how many places to the right? 3, which means I'm multiplying by 10 cubed. So I need to multiply this by 10 cubed. So my numerator no longer has that decimal in the middle of it. My denominator is 999 with how many zeros? If you multiply by 10 cubed, you add 3 zeros. Let's get our commas in there. And I have, well, I know that can be reduced, right? How do I know it can be reduced? Bryce, how do I know it can be reduced? They're both even numbers. Let's do it the easy way. Type in 1,030,512 divided by 999,000 and see how much the calculator reduces it. Pascal, you need to be typing it in on your calculator also. Coleman, what'd you get? Okay, slow down. Let me catch up. Okay, over. Others get that? So it was divided by more than just 2. Much easier when we can use a calculator to simplify it. Does anybody have questions on repeating decimals, writing them as fractions? Terminating decimals, writing those as fractions? Or our subgroups of the complex numbers and the different abbreviations for those? All right, then we'll work on homework.